Thank you very much. Good afternoon, everybody. I'd like to thank the organizers and you for coming here today and to discuss about stars. As Chris said, about 3 months ago, I've been here for talking about physics, which might be known for all of you. And I'm going to review about that briefly. And then I'm going to talk about stars, which are been maybe a question for 1,000 years from our ancestors, us, and even maybe the next generation. I'm going to talk about stars' life. How do they born? How do they live? And in the end, how do they die? So today, the contents of my talk is going to be, firstly, let's define a star. What is a star? And how they are created, and from what they are created. And we'll see that what happens when they die. And in the end, I'm going to talk about our solar system and the sun. And by the way, the last question is you guys have to answer. Because don't worry, I lead you in a way that easily you will be able to answer what's going to be the fate of our solar system. So you can see this picture. All of us have seen with naked eyes, or maybe some of you had the chance to look at the sky with telescopes. These are stars, and I'm going to ask you now, in your opinion, what is a star? Let me know. Who knows what is a star, or who can define a star, actually?
Kobe?
Yeah, please.
A ball of gas or something?
A ball of gas, okay.
The sun.
That's great. Any other idea? Yes, please. Yeah. Yeah. What do you think? What's the star?
A burning ball of gas?
A burning ball of gas.
Made up of different combination of gases.
Nice, nice. So I'm going to say in a maybe very easy way that a star is a giant luminous ball full of superheated gas. But again, we have to discuss about what are superheated gases and what made them to be superheated. Okay, as I said, I'm going today to talk about the life of a star, but I want to say that stars are really similar to us. They are born, as I said, they live for a while, and in the end, sadly, they die. But actually, it's not sad for us, because at the death of the stars, the explosions that I'm going to explain and the death of the stars made the elements in the universe to be distributed, and we have those elements in our body. So it was the source of life also. And that's why the astrophysics or astronomy is one of the interesting topics and useful topics for us to learn. So how a star is born? A star are born inside a cold, dark cloud of dust. So when I say dust, I mean cosmic dust, not the normal dust that we have on Earth, and hydrogen gas. So maybe in a very professional way, we call it nebulae. And this makes them the gravity makes them actually to pull them and to contract them and to make them in the shape of a disk, which we call it a protostar. It means it's like at the time that a star is going to born actually. When we call it protostar, it means that the star is at the time to get born. But let me go back to my slide, and I said here that it's full of hydrogen gas. So I'm going to ask you, what is hydrogen? Have you heard about it? Yes, please.
Like for bombs?
Sorry, loudly, please.
Like for bombs?
For bombs. Okay. Yeah, please.
Hydrogen is like in balloons.
Hydrogen is like balloons, okay.
It's lighter than air.
Okay, lighter than the air, you mean?
Yeah.
Okay, good. Any other idea? What's hydrogen? How do you define hydrogen? Okay, you know, hydrogen, I can say, is the most abundant element in the universe and the simplest one. So, you might see this periodic table in your science or maybe chemistry books. This periodic table has been made by the efforts of Soviet chemist and physicist Mendeleev, and hydrogen exists here. I can say hydrogen consists of a proton and an electron that is orbiting around it. A very simple structure. So you can see the mass of a hydrogen in atomic mass unit, which I'm going to explain you later. And we know that, as I said, you know, stars are like us, you know, and they need some fuel to live, you know. Like, for example, us. All of us ate our lunch today, and to get some energy and other stuff that our body needs. Actually, the nuclear fusion is the fuel of the star to live. But I'm going to explain you what is a nuclear fusion in an easy way. Of course, nuclear fusion is not so easy to understand and requires many mathematics and physics. But in an easy way, okay, let me to divide these two words and open them up and define them. What is the nuclear? When we say nuclear, we mean that the process which involves nucleus. And when we say fusion, we mean that we want to make and mix two or more entities and make them belong to each other and make one entity. That's called the fusion. So, in an overall, I can explain it in an easy way. It's the combination of the nuclei. So, nuclear fusion becomes the combination of the nuclei. And in a scientific way, we say that a nuclear reaction which the lighter elements are combined to each other and going to make the heavier elements, actually. So I'm going to repeat again. The lighter elements combine with each other and make the heavier elements. So this is actually the main reason that stars are alive. And that is we can call it a fuel of a star for its existence. So now I'm going to give you a very maybe a simple example of the nuclear fusion, but it might be weird for you, you know. So don't worry if you don't understand it. When we combine two hydrogens, right? So now these two hydrogens has been combined to each other, and it gives us an isotope of the hydrogen. Hydrogen, sorry. And then it gives us a positron. So don't worry, a positron is just antimatter of the electron. It means each particle in the universe has its antiparticle. So we can call it also anti-electron. And the neutrinos. So neutrino is a subatomic particle. So for the moment, let's forget about these two parts and focus on this. So two hydrogens mixed up and made deuterium. We call it deuterium. Actually, these 2 and 1s are the number of protons and neutrons, and here is just the number of protons. So as I've shown you, and you saw that a hydrogen just consists of 1 proton, an electron it's orbiting around it. But deuterium has 1 proton and 1 neutron. So when this is gonna be summed with another hydrogen, it's gonna give us an isotope of the helium. And in the end, these two heliums mixed up, and it's gonna give us this helium-4 plus two hydrogens. So this is actually how the stars are getting fused to each other. So in an other example, I can say that 4 atoms of hydrogen are going to give us helium plus 2 positrons and 2 neutrinos and energy. But I want to call it a very huge amount size of energy. So here, let's do few easy calculations.
Hey Milad,
Yeah.
question for you
Yeah.
before you go into the calculation.
Yeah.
Someone here asked a question.
Yeah.
Do the elements create space? So here you were mentioning helium and hydrogen, which are both elements,
Yeah.
and how those kind of interact to create the nuclear fission, which turns
Yeah.
into the star.
Yeah.
Is it fair to say then that the elements are what the star is made out of?
Exactly.
Can you also say that is space also what elements?
It depends on what you define space. You know, for example, 13.8 billion years ago, our universe has been started by Big Bang. And at that time, it was nothing. And then suddenly, due to some physical reactions, the hydrogen has been distributed around this universe. And they become like a cloud. I mean, a million years or billion years take time, you know. So then they have been like a cloud. And because they were heavy, so they have been like with gravity, they have been mixed up with each other. You know, and when they're mixed up, it means that the gravity is pulling those hydrogens, and you know it's making a disk, and that huge amount of gravity is making them to collide to each other. So that is actually the fusion, and it's going to make that heliums when they collide to each other. So they are making helium. Helium when they collide, you know, we need a huge amount of temperature actually. So that's why I'm going to do these calculations to tell you how, you know, these easy equation that I've already mentioned here, I will let you know that how much amount of energy is going to give us. It's just mind-blowing. So let me just do just write down what it's written here. So for hydrogen is going to give us helium plus 2 neutrino plus 2 positron plus energy. Right? Can you see it? Can everyone see it? Okay. So I've shown you that the mass of the hydrogen is about 1.0078, and of course 4 is going to be multiplied to this, and it's giving us 4. Thank you very much. It's going to help a lot. Atomic mass unit. Atomic mass unit means that the exact mass of 1/12 of the exact mass of the carbon 12. So don't worry about these units for the moment. Maybe it's going to be difficult. So then let's go to here. The mass of the helium is going to be 4.002604. The mass of the positron is equal to the mass of the electron. So it can be negligible, but let's do it. 0.00058. So in order to get the difference in the mass, so we add them up and we subtract from this, right? So it's going to give us approximately 0.0274 AMU. So let me just convert it to the electron volt. It's going to be 931.5 mega electron volts, which it's going to give us 27 mega electron volts. So this has been the energy released from this simple equation. 27 mega electron volt. Let me convert it to the Kelvin or the Celsius. So I just can say 27, I mean, each mega electron volt, 1 mega electron volt equals to approximately 10 raised to 10 Kelvin.
What is that in Celsius?
So 0 Celsius is equal to 273 point something Kelvin. So not that difference. So we can just say, okay, even just 10 raised to 10 Celsius. So imagine now 27 mega electron volt means 27 into 10 raised to 10 Kelvin temperature is going to give us.
So it's kind of hot. Yeah.
Yes, super hot.
Yeah.
Right? So then imagine, so this is for the time that hydrogen is going to get fused to the helium. And if the star is massive enough, so this helium is going to go and, just to fuse to carbon. So I will explain later. That's what I want to say, that all the elements that has been created and now we have on our planet and in our body has been made in stars. So, okay, this calculation has been done. So the life of a star, the lifetime of the star is determined by the amount of the fuel and the rate of the consumption. So it depends on how much fuel we have and in what rate it's gonna burn actually. But it's also denoted by the balance between two forces, the gravity force and the pressure. Let me ask you first, what is pressure? Do you know what is pressure? Have you heard about it before? What is pressure? Okay, all of us are living in Japan. Okay, let me give you a very easy example. When you go to some restaurants and you just order miso soup, right? And then the person who is working in the restaurant is kind enough and just put some cap on your bowl just to avoid, like, for example, this miso shiro becomes cold until it's gonna reach you, right? So, but have you just noticed that when you want to open it, it's quite difficult to open it, right? Have you tried that? Have you experienced that? So why is that? I just can say, again, the pressure, which I'm going to show by P, is the ratio of the force acting on the area. It means that, let's imagine this is just miso shiro. I'm very bad in drawing, I'm so sorry. But, okay, this is just the miso shiro. It means that these particles, this heat, are just gonna hit this cap, right? So it's too much. But the particles that are hitting this are not equal to this, right? Because we are just in a normal temperature, like the room temperature, and these particles are a bit far from each other, right? But when it's hot here, so the difference on the amount that the heat makes us to get difficulty to open this. So that we call, the amount of force that it's exerting on the area, we call it the pressure. So when the fusion is happening, actually, so as I said, the huge amount of dust we have, the gravity, because it's heavy, or massive, I can say, that the gravity is gonna pull it towards to itself, to the core, but the pressure, which it's made due to the fusion, it's going to just push. I just can't say in an easy way again, like a smoke, right? The smoke is just going up, right? They don't want to get to the center, right? So the smoke is going up, but the gravity wants to pull it. Actually, this balance is gonna make a star to be alive. It means that until the fusion is happening, it can overcome the gravity. Otherwise, when the fuel is over, it cannot just, it's just, I can say, it's just pushing from down to up, and this side is just pushing from up to down, right? Just they are somehow balancing each other. If we miss one of them, what's gonna happen? Of course, the balance is not gonna happen, and the star will collapse. right? So this is the most important part that you have to, remember. Okay.
Milad, quick question.
Yeah, please. Yeah.
I want to ask, what is the difference between big stars and small stars when they're born? Does gravity and pressure make?
It's actually the amount of the cloud, the amount of the gas cloud and dust that the star is just born from that. The amount of that cloud, is making the star. As bigger as it is, of course, the star is going to be bigger. And if it's small, but of course the mass should be, in a for example, a specific, amount. And to pulls out, it takes like millions years maybe to pulls out. And that gravity, is just trying to make a disk, as I said. And it's just going to make it very fast. Fast means heat is high. It's too, the temperature is too much. And that actually, maybe intentionally I didn't explain something to you. Sorry, let me. Because I was expecting that question, I said hydrogen made by proton, right? An electron that is orbiting around it. When it's heated up, the electron is just going to go away. And I said that, okay, so the one proton is going to remain and another proton is going to remain, right? So all of us know from elementary school that positive and positive cannot attract each other, right? They repulse each other. So what happened? Why do they do that? The answer is because it's so dense and hot. So hot means they are so moving fast. So then they just call it to each other. That's the reason. If it's not that hot or it's not that fast, it means that it never can make them.
So in the same way, you can take two positively charged magnets,
Yes.
move them quickly and
Yes.
touch, but slowly they won't.
No.
Same idea.
Yeah.
Okay.
So, the fate of the star depends on, let me just, before going to this, talk, let me explain you, or just share my opinion with you. As I said, that stars are like us. Very much similar, I personally think like that. But the fate of human depends on, I personally think, maybe you guys have another idea, I personally think that the fate of a human depends on how much work he does. Right, for example, or how much effort he does. For example, if you want to be an athlete, or just like, for example, in 2020, you want to win the gold, medal in just Tokyo Olympics, you have to work hard, or at least you have to do that much that, the others didn't do, right? So, but the fate of the stars doesn't maybe based on how they do. Actually, the fate of a star depends on its mass. So it means that, as I said, when the cloud that the star or the nebulae that the star has been made of is massive enough, totally the fate is going to be different than for example, the cloud that the mass is not that high, right? So remember also, the fate of a star depends on its mass. So, okay, before going to the next slide, I want to ask you, of course this is a star, but what do you know, can you guess what star is this? Sun. So sun is our star, right? So it means we are living in a system which we call solar system, right? And some planets are orbiting around the sun. Right? Do you know what planets? Okay. Yes, please. Yes. Okay, maybe it's a good idea if I share a simple way for you guys to remember those planets. I didn't bring it in my slide, but I can write it down here. By this sentence, my very educated mother just served us noodle In India, we were calling naan or whatever you want. So it depends on how you like. So my goes for Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Around 10 or 15 years ago, I don't remember exactly, but when I was undergraduate, the Pluto was still a planet. But suddenly I just saw in the news that Astronomical Union just kicked it out because they thought that it's a dwarf planet, actually. It's not a planet. Anyway, so why I brought the sun here, just to introduce you just the new scales. From now on, I'm going to explain you the mass, that we are going to care is related to the mass of the sun. So the mass of the sun is approximately 2, but here I just wrote the precise number, 1.989 into 10 raised to 30 kilograms. 10 raised to 30 kilograms means how many zeros after that number? 30 zeros, right? It means it's so huge. Or it's 333,000 times of the mass of the Earth. And the radius of it is about 109 times radius of Earth. So this, please take care of this notation. In professional astrophysics, we just use these symbols for sun, and this one is for the Earth. We don't want to write, maybe it's because we are lazy. Okay, so as I said, the fate of a star depends on its what? Mass, exactly. So now I prepared 3 different paths for a star. It means that, for example, what's going to happen to the star? Okay, let's just check it in 3 different ways. The first way is when the star is 0.128 times solar mass. Okay, let me review it. 2 into 10 raised to 30 kilograms, right? So it means that 0.1 into 2 into 10 raised to 30 means how many? 0.1 means 1 into 10 raised to minus 1, right? Let me write down again. So when we say 0.1 into 2 into 10 raised to 30, so this 0.1 means minus 1. So this minus 1 and this will cancel out, so it's going to be 10 raised to 29, right? Okay. So this is the first path that we are going to talk about, and the second is going to be 8 to 25 solar mass, and the third is going to be 25 to 130 solar mass. So very big, right? Huge, actually, I can say. So let me focus on the first path at the moment. Okay, I just brought this figure again. This is just the balance between the gravity and the pressure, right? So here, I've also prepared the different paths between. May you please kindly just switch off the, yeah. Yep, thank you very much. So 2 different paths are there. Actually, this is 3, but we are going to here, and these 2 also are going to be different. So the first path is for those stars that are not so big. Almost, I can say, our sun. So what's going to happen? As you can see here, when the hydrogen is burning, it's fusing, it's going to be helium, right? So hydrogen is going to go to helium, and it makes the star bigger and bigger. So then the color is going to be changed, and we call it red giant. Giant, of course, means big, and it's red. So as the sun is getting older and older, and it's fusing, so the size of the sun is increasing. It's getting bigger and bigger. So a star is running out of the hydrogen, means it's burning, it cools and gets bigger. After that, planetary nebula will happen. As I said, this is the star, and it's just going to expand and expand, and it's getting bigger and bigger. And it goes to where? It goes to the interstellar medium. Interstellar medium means that whatever we have between two stars, okay, this is one star, this is another one, the medium, whatever it is between them. So it's going to expand. What do we have here? Of course, it's expanding, and until they dissipate in the interstellar medium. And this is going to turn, actually I want to show here, just the core will remain, and we call it white dwarf. This one. So among of these big amount of, nebulae, what remain is just a small part, which we call it white dwarf. And the rest is just gonna go out of the interstellar medium. So this star is gonna be small, super dense, and very high in temperature. And it gets like billion years to get to black dwarf. But here I'm going to ask you a question. Why does it take a billion years? Can you just discuss with each other?
So take a moment, turn to the person next to you,
Yeah.
and think, why does it take a billion years for, what is it again, for a
white dwarf to turn to black dwarf? I mean, just it gets colder, maybe?
Go for it. Take a minute to chat with each other.
Yeah.
Try to create as many possible combinations of the particle, and the heat gets out longer than the universe would make sense. You can make
Okay. Any answer? Yes, please.
I think it takes a billion years because it takes a very long time for the star to cool down
Yes.
from the black dwarf.
Yes. It's a very nice answer, but it could be more precise. But good job. Any other idea?
Cookie.
Yes, please.
Right, but like in car engines,
Mm-hmm.
like when you ride and stop, the engine is still hot,
Mm-hmm.
and it takes time to the engine to slow down, and when it completely stops, it becomes cool, and that is the black dwarf.
I like the way you think, but whenever, as I said again, the fate of a star depends on its mass. So I said white dwarf is not that massive. So when it's not that massive, it means that the gravity is weaker with compared to massive stars. When the gravity is weaker, it means that the fusion and the fuel is gonna just take time, just to burn. Right? Because as much as it's bigger, the core is more active, the interactions are much more, right? With compared to the smaller ones. When they are small, they are much more slower. Actually, I can say, for example, giant stars take million years to get to the end point of their life. But the smaller stars takes billion years more, right? And for example, as I said, for a white dwarf to turn to the black dwarf takes hundreds of billion years. But the age of our universe is just 13.8 8 billion years. So it means it's much more than the age of a universe. Right? Interesting. Okay. I'm going to the second path. Second path is about 8 to 25 solar masses. And again, here, the stars are larger, right? The previous one was 0.128, but now it starts from 8 to 25, right? So the stars are larger and make, they are larger, so they are shorter. I mean, they just die shorter than the smaller stars, and they make red supergiant, not just giant. So it's bigger. If you compare these two with each other, so this, in the second line we have just a bigger one. So it's larger, and of course it's more luminous, right? And the next step is gonna be the supernova. Supernova is a violent explosion of a star at the end of its life. You know, the funny thing is that supernova literally means, super means of course very big, nova means born actually. Previously the scientists were thinking that, okay, at this time, when this explosion is gonna happen because it's so bright, which it's gonna like make light an entire galaxy. It's that much violent and big. So they were thinking previously that this is a birth of the star, but actually not. This is the end phase of the star. So, as I've written here, stars blow off its outer shell into interstellar space and may shine the entire galaxy. So, what's going to happen here actually? As I said, hydrogen is going to burn to helium. Helium is going to burn to get carbon. Carbon is going to again fuse. We get oxygen. And you see, please, the time scales. For hydrogen to get to helium, 7 to 10 raised to 6 years. It means 7 mega years is going to take time. Right? And helium, to be like carbon, to go to carbon, to fuse to carbon, 7 to 10 raised to 5 years. And again, for carbon to oxygen, 600 years. Oxygen to silicon, 6 months. Silicon to iron. Iron, can't fuse anymore. Iron is the most stable element in the universe. So, remember the picture that I was insisting, this one. The balance between gravity and the pressure, right? So what's going to happen here? So when we reach to iron, there is no pressure because there is no fusion anymore, right? Iron won't burn anymore. So it means that, okay, this pressure is just going to drop down. What will remain? Huge amount of gravity. So it makes all the material collapse into their core. So that's what we call it, core collapse supernovae. That's actually the violent explosion of a star.
Quick question.
Yeah.
Someone had asked, what exactly do you study about stars?
Okay.
And if I remember correctly, I think that's it.
Yes, exactly. So, yes, supernovae. Let me explain briefly that what physics is gonna do. Physics is a type of is a branch of science that is caring about the nature and the origin actually, and also the origin of the nature, right? So of course it has different branches, which is just making me interested about is astrophysics, means that the physics of the stars and the heavens. So all branches of physics have two different branches also, theory and experiments. So in astrophysics, we cannot do any experiment here, on Earth. So it means observational. So when the observational data and the theory data are just going to be same to each other, at that time we say physics has approved it. So why did I give this introduction to you? Because supernovae even been, observed like 1,000 years ago by Chinese ancient books. But, okay, we detect, but theoretically also we have to try to find it out and figure out what is the physics of this explosion. Unfortunately, many years it's happening, and still the scientists are not successful to calculate and to understand mathematically and theoretically, and even by simulations and by the computers, the physics of supernovae. So we are trying to investigate that. And I particularly am studying the oscillations of the neutrinos. It means that those subatomic particles that play a very key role, if you remember in that equation, so electron neutrinos has been released by that fusion, right? So that neutrino plays an important role in the explosion mechanism of the supernovae. So I do understand the behavior and the physics of the neutrinos inside this core. And I try to calculate analytically and apply it to the computer and make it explosion. Of course, it's very difficult. So we are at least trying. Yeah, this is what I do. So, okay, so after the violent and huge explosion, which we called it supernovae, what do we get here? Again, depends on the initial mass. We get neutron star. The neutron stars are small and very compact. I can say that small that the radius of a neutron star is about 20 or 10 kilometers. Yeah, the diameter is going to be, just if you're comparing the Manhattan, the neutron star can be this much. But it's so dense, and the mass of the neutron star is heavier than our planet even. And as a comparison, I can say a cube in neutron star is equal to the mass of the Everest mountain. A cube in this star, just sugar cube maybe size, is that much dense, because of, as I said, the core was so, active, was so fast, and was so hot. So they were just contracting each other. So the density is so high in that star. So a cube in that star is approximately equal to the whole amount of the Mount Everest. And also, they spin so fast, and the spin is just making pulses. That pulsar stars are also coming from them. The third step and the path is going to be the stars that have 25 to 130 solar masses. Again, let's go to this balancing and this way. So here, we get to this side. So again, the initial paths are almost the same. Let me tell you something also, that the supernovae are also going to happen in different types. We don't have one type of supernovae. I'm not going to go to that different types of supernovae because it might be confusing, and maybe it's just I have to come here maybe for another time just to explain about the different types of it. So because of the time limitations, I just skipped that one. But just be aware about that we have different types of supernovae. And again, the stars are large, as I said, and we get the red supergiant again, which is large and more luminous. And we get supernovae again, and the same way, but because it was much more massive, we get black hole at the end of this phase. Black hole is also having very high density, and nothing can escape from black hole actually. To be honest, understanding of the black hole is still mysterious and one of the most difficult things in the universe. And no one can say that the mechanism of the black holes has been well understood. So now I'm going to turn a question again, and I want you to discuss with each other that can we detect, by the way, this picture is an artificial picture. This is not a real one. So I want to say why, okay, not why, just can we detect black holes, or can we observe black holes? Discuss with each other and then reply. Or before asking before answering, not even because I asked you already, before answering that question, can you let me know how can we see something, or how can we see an object, please?
When light hits it and
when light hits and reflects, you mean?
Yeah.
Okay. So then can we observe black holes?
No.
No. That's the answer. We can see something when we get some light from it. Otherwise, we cannot see it. But how do we know? Yes, please.
We can't see black holes because light can't escape from it, so it can't reflect.
Yes. And whatever goes in it, it just goes inside, it sucks it, and never let it to escape. Whatever, even light. You can, if you can, for example, if you just imagine now I'm just going towards this black hole, okay, and when I just go inside. Only I can just escape from this black hole when my speed is more than the speed of light. Do you know what is the speed of light? Approximate level, just 3. We show it by C is 3 into 10 raised to 8. Or I just can say maybe more precisely 10 centimeter per second. It's too fast, right? So let me repeat it again. And this is the maximum speed we have in our universe. And physics based on this, that the maximum speed is the speed of light, right? So I said I can only escape from this black hole when I have the speed more than light. So it's impossible. I never can escape from here. So whoever goes, just go in. And what's going to happen to us, no one knows. Yes, please.
Yeah. What are white holes? Like I've heard of them before.
Okay. So white holes are just, we can say that they are just in the opposite way of black holes. So I said what? We cannot escape from it. But in white holes, it's vice versa. You can't go in it. It's just opposite, direction of the black hole. That's what white hole. And of course, it's just, based on general theory of relativity and bit mathematics and stuff requires. Maybe when you get a bit more advanced in mathematics, you definitely can understand that.
Would you be able to simply answer what happens to create a black hole versus a white hole? What's the main factor that causes? Actually,
I have to explain the Einstein field equation. So it's not that easy, to talk about it now. Yeah, because until the new century, we had difficulty to understand the mathematics of the universe. You know, Einstein changed our mind and our understanding about the nature by introducing a new type of mathematics, actually. So that requires to understand. Okay, so let me say again. Okay, so now another question. So how can we detect, or how can we understand, okay, for example, this part of the universe, we have black hole. How can we estimate it? How can we understand? Do you have any idea? Okay, let me repeat. I said, okay, we never can detect it. We can't because it's black. So, for example, imagine everything is just now, all the lights are off, and even the curtains and everything is just totally closed. Even we can't see each other, right? So then, okay, acceptable, black holes can't be seen, but how can we, for example, say, okay, at this point of the universe or sky, we have black hole. How can we understand? Yes?
Because we can observe objects being sucked into the black hole, but we can't
Perfect.
see them.
Yes. Usually stars are in binary. Right? And then imagine, for example, just a star is just orbiting around each other. We call them that they are in binary system. They're just orbiting around each other. And they're so common also. Imagine, okay, collapse happened and one of them are black hole. So because of the gravity, all matters from another star is somehow sucked into this black hole. So then we can observe by that, and it makes a disk. You know, it's like you know, when you just, for example, open a water tap and just when it's going down, you know, it's just orbiting. So it's somehow like that. It makes so dense, so hot, and they emit and radiate some sort of radiations again. So by that, yes, she's perfectly correct. By that way, we can understand, yes, we have those black holes around us. Okay, so if you remember, in the first slide, I asked you, or I made a question that what is the fate of our solar system? And what is the end point of our solar system? I'm going to ask you now the question again. What is going to be the fate of our solar system by the definitions that I've already given to you? Discuss with each other.
We're just talking about our solar system, then we're going to be engulfed by the red giant.
Any answer? I'm pretty sure you know the answer. So I said the sun, our sun is a type of star that, okay, let's call it normal star. So what was the fate of the normal stars? Yes.
So first it would turn into a red giant and it would engulf maybe the first 4 planets.
So it means the sun becomes bigger and bigger and bigger and bigger and bigger, comes up to here.
And then it would explode, I guess. So then Jupiter, Saturn, Uranus, and Neptune get
And the sun is gonna be
a white dwarf.
yes, a white dwarf. And it's gonna take billion years. Yes. That's gonna be the fate of our solar system because of the structure of the sun. First, as the sun, the hydrogen and it just fuses, it turns just to be, to come towards the planets, I can say. And maybe it might just goes up to the radius of the Mars. Then the white dwarf will remain from our sun. But it takes billion years, yeah. Okay, so
Kofi, you have a question?
Yes.
yeah, please.
Like, if the sun is like a large star,
Yeah.
like what will happen? Like, if it just expands, will it just go to Neptune?
So you mean that if the sun, for example, at the beginning is like, for example, a huge star, right? So at that time we weren't here. The life wasn't exist. Right? And of course the structure of the planets were different also. Yeah. Another question. Imagine, okay, now this is sun and all the planets are orbiting around the sun, right? Imagine this sun becomes a black hole. Just imagine. Do you think it sucks all the planets? What will happen?
I think when the explosion happens, all the sun will just.
Okay, imagine the explosion happened and just we have black hole now and all the planets are orbiting around the sun. What's going to happen? Do they orbit normally or they just all just being sucked to the black hole? What's going to happen? Discuss again, please. Yeah.
I thought it would like change its orbit that much.
Kind of similar.
Yeah.
I might have some.
Yeah.
I think it's just when it's orbit on the leg, then like would it
Is it done? Yes, I'm ready. Any answer?
Maybe a quick show of hands.
Yeah.
Who thinks that all the planets would be sucked into the black hole? Raise your hand. Couple people. All right. Who thinks that the planets would continue orbiting normally? Okay. Who thinks something else would happen?
Okay, what will happen?
I think they'll orbit around the black hole and slowly get closer to it, and then in the end.
Okay, good imagination. I liked it, but no, nothing will happen. Just the planets are going to orbit around it normally.
And why is that?
But just because of the gravity. As I said, the black hole will suck. When you go to a horizon of the black hole, we call it a horizon. When you go to a certain, radius of the black hole, then you'll be sucked in. But if you're far away, so you're safe.
So right now the current distance between Mercury and the Sun is too far for that
Yes.
to be all right.
Yeah.
So someone asked the question, I
Yeah.
should say, in the future, do you think black holes would eat the universe? With the the answer then be no?
It's really difficult to answer because I think not me, even no one knows it. But because that's why I wanted to bring after this. Yukawa is a very famous Japanese physicist, which claims that reality is complicated, and also there is no justification for this. So what I want to say is, there is some possibility that we might get something wrong, and our understanding about the structure and everything is again not correct. As previously I talked about Aristotle, and one of you asked me, do you guys in science community make fun of Aristotle because all his theories was wrong? For example, his theories on light, his theories on how do we see the objects and stuff, all of them nowadays are just, a funny theory. But honestly, we do respect Aristotle by his great ideas. And at his time, he was, I just don't want to say the best, but one of the best scientists in his time. So what I want to say here is, science might change, firstly, and about the future, as far as we know, is, all the universe, if you want just to say a universe will be sucked to a black hole, maybe I can say I don't know, Yes. Okay, this is the end of my talk actually, and thank you very much for listening to my talk, and please don't hesitate to ask me any question.
All right, well,
Yep.
Let's give Milad a round of applause.